Welcome to a review of some right triangle trigonometry from geometry. Thought it would be a great way to kind of just start off the year with something that we knew. Since this is the first official video of the year, I just want to remind you of the following. You can pause this video at any time. If I'm going too fast, you can pause it to write down what you need. And in fact, you can even rewind if you need to review something. So even though learning by a video is not ideal, no, those are some benefits that maybe you don't have in the regular classroom. One thing that maybe could be a benefit, again, yes, I'm trying to make a little lemon out of lemonade here. Or lemonade out of lemons, excuse me. One of the things that is helpful for some kids is that you can fast forward. Like, I know it, I get it, I don't need to listen. Okay, make sure you really don't need to listen. I wouldn't fast forward all the way to the end, but you can fast forward if you're like, hey, I know where she's going with this. I've done these problems before. And sometimes I even like to mute myself. Often when I am reviewing or trying to learn something new and I'm doing it from a video, if it's math related, I like to mute it, see if I can do it at my seat, and then either join in when I'm ready to see the answer, or again, I can pause, rewind, fast forward as needed. So just a reminder of those tools that you have when you're learning by a video. All right, here we go. So we're going to go back to basics. We're going to talk about the parts of a right triangle. For all intents and purposes, the trig we're going to be talking about in the next 2 units will have to do with right triangles. You did learn a little bit about non-right triangles at some point, depending on your background, maybe a geometry class or algebra 2 trig class. You did discuss law of sines and law of cosines. So those are tools we can use with the non-right triangle. But again, for all intensive purposes, we're going to be talking about right triangles. So in a right triangle, what makes it right is there's a 90-degree angle. And the side opposite that angle is always the hypotenuse. The hypotenuse is never considered a side to the triangle. The hypotenuse is the longest side of the triangle, and it is always across from the 90-degree angle. And in this case, it doesn't make a difference if theta is where I have it or if theta is up here. The hypotenuse is always the hypotenuse. Now, if I want to discuss this angle, so I'm using angle theta. If you don't like theta, you can use x, y, any variable. But often we use lowercase letters of the Greek alphabet. Sometimes you'll see alpha used, occasionally a beta used. And those are just to denote an unknown, and we use them in regards to angles. If I trace that angle, so if I trace angle theta, this side is the hypotenuse side. The hypotenuse side cannot be a side. That means the side that is creating it or that's touching it, this is your adjacent side. And then by process of elimination, the side that is across from angle theta that is not touching it is your opposite side. So now we can compare these sides and create ratios. We have special names for these ratios. All right, if I have my triangle and I want to compare the opposite side to the hypotenuse, so the opposite side to the hypotenuse, we call this the sine ratio. If I have a right triangle and I want to compare the adjacent side to the hypotenuse, we call that the cosine ratio. And last but not least, if I don't want to compare using the hypotenuse at all, and I just want to do the opposite side over the adjacent side, we call that the tangent ratio. So hopefully you remember SOHCAHTOA. That was kind of a way to remember those particular ratios. All right, hopefully those are a review from geometry. And it just, depending on your background, a reminder that there's 3 additional trig functions. And I'll be frank, I don't know that I don't really memorize this. I don't memorize that cosecant is hypotenuse over opposite. I know that. And I know that the secant is the hypotenuse over the adjacent and the cotangent, but that's 6 different things to remember. What I remember is that cosecant and sine, those are reciprocal pairs. So if I know that the sine is opposite over the hypotenuse, then I know that the cosecant is a hypotenuse over opposite. Again, I remember that secant and the cosines go together. How do I remember that? Each pair, one of them has a co. So the cosecant has to go with the sine that doesn't have a co. The secant doesn't have a co, so it's got to go with the cosine. So if I know that cosine is equal to the adjacent over the hypotenuse, then I know that the secant is hypotenuse over adjacent. And last but not least, the pair that makes sense are cotangent and tangent because they sound alike. So again, I don't know that I memorized that cotangent is the adjacent over the opposite. I use my SOHCAHTOA, and if tangent is opposite over adjacent, then I know that the cotangent is adjacent over opposite. So as a reminder, a ratio is just a comparison of two items. If we had 7 boys in the class and we had 8 girls in the class, then the ratio of boys to girls can be written as 7 to 8. You can write it using the English word, or sometimes you can even use a colon to discuss a ratio. I would say for our intensive purposes, that's what we're going to use most often. All right, so again, this is SOHCAHTOA, just written out. This is just a way to remember these ratios. The sine is the opposite over hypotenuse, the cosine, and you need to spell it like a true St. Louisan. SOHCAHTOA. You know, people sometimes they wash their car or they drive on Highway 44 and park with the FARC. And not to be confused with, a Boston accent where, we park a car in Harvard Square. But nevertheless, cosine is the adjacent over the hypotenuse, and tangent is the opposite over adjacent. All right, so let's do our first example. All right, I'm trying to pinch in, and instead it keeps wanting to write. So we're going to evaluate the 6 trigonometric functions given angle theta. There we go. All right, so let's think about this. You do not have to do your work like I do, but this is how I organize. I have the sine of theta, the cosine of theta, and I have the tangent of theta. And what I write across from them are their reciprocals. The sine goes with the cosecant. The cosine has a co in it, so it goes without the co and the secant. And then tangent and the cotangent are the ones that match. Well, in order for me to get sine or cosine, I have to know the hypotenuse. This is angle theta. 5 in relationship to angle theta is your adjacent side. 10 in relationship to theta is your opposite side. So that means I have to find the hypotenuse. Well, what tool allows you to do that? Pythagorean theorem. 5 squared plus 10 squared equals your hypotenuse squared. So that's 25 plus 100 is equal to the hypotenuse squared. We're going to have to take the square root. And while I know that it is equal to a decimal, we're not going to use decimals. Decimals are not exact. So again, decimals are not exact. So we're going to keep this in simplest radical form. I can think of 125 as 25 times 5. So this is going to be 5 root 5. All right, so let's do our sine ratios. I'm going to get rid of this so that we have a little bit more room. All right, so I know that the sine is so O over H. Opposite is going to be 10 over the hypotenuse of 5 root 5. And I know that this is going to reduce, and I'm going to reduce it in just a second, but I want to encourage you to go ahead and flip it now. Why? Because it's less rationalizing. If you rationalize now, you're going to have to rationalize cosecant all over again, and I could just get root 5 over 2, and I'm done. I'll go back and simplify the sine momentarily. Cosine is adjacent over hypotenuse, so that's going to be 5 over root 5. Again, I will simplify that shortly, but if I go ahead and take its reciprocal now, I just get root 5. Oh, that was kind of silly. There we go. And my tangent is going to be TOA. So opposite, which is 10, over adjacent, which is 5, that gives me 2, and the reciprocal of 2 is a half. So again, instead of having to remember what cosecant and secant and cotangent are, my strategy is to figure out sine, cosine, and tangent, and then just take their reciprocals. Now, we do need to simplify 10 over 5 root 5 and 5 over 5 root 5. So in those cases, this becomes 2 over root 5, and 2 root 5 when I rationalize becomes 2 root 5 over 5. And now let's do cosine. Cosine is 5 over 5 root 5, which simplifies to 1 over root 5. And I get root 5 over root 25, which is root 5 over 5. So that's my answer to problem 1. Problem 2 is a very similar problem. They just didn't give you the picture of a triangle. They tell you that theta is the acute angle of a right triangle and find the values of the other 5 trigonometric functions of sine, or of theta, excuse me. So let's do my chart. I have the sine of theta, I have the cosine of theta, I have the tangent of theta, I have the cosecant of theta, which is 10/7. They already gave it to me. I have the secant of theta I have to find, and the cotangent. So I know that the sine is 7 over 10. Got that pretty quick. But now we have to find the other 4. So I like to make this visual. I'm going to go ahead and I'm going to draw a right triangle. And you may assign theta anywhere you want. So again, I know that the sine is opposite over hypotenuse, so that means my opposite is 7, 10 is my hypotenuse, so I'm going to have to do Pythagorean theorem. This time I know the hypotenuse, so it's 7 squared plus my adjacent side squared is going to equal 10 squared. So 49 plus a squared is equal to 100. So a squared is going to be equal to 51. So a is equal to root 51. And I don't believe there's a perfect square that goes evenly into 51. All right, let's go. Your cosine is going to be adjacent over hypotenuse. So that is going to be root 51 over 10. And your tangent is going to be 7 over root 51. And again, I'm going to wait to rationalize that because if I just flip it now, I get root 51 over 7. That's less rationalizing. And if I do the secant, I get 10 over the square root of 51. So I'm going to have to rationalize the secant and the tangent. And so when I multiply by root 51 over root 51, I get 7 root 51 over 51. And similarly here, we're going to get 10 root 51 all over 51. Okay, let's evaluate the trig functions of 45. And sometimes kids go and they're like, how am I supposed to do this? You have your special right triangles. If you have a 45, 45, 90 triangle, this is a right isosceles triangle. So the goal is that whatever side you have making up your 90-degree angles, they're the same. So guys, you might as well just make them 1. You can make them both 2, you can make them both 3, you can make them both 4. Who cares? Because everything will still reduce. So if I take 1 squared plus 1 squared equals my hypotenuse squared, that means that your hypotenuse is going to be the square root of 2. So what is the sine of 45 degrees? Well, you can pick either 45 degrees because no matter which one you pick, the opposite is 1 and your hypotenuse is 2. When I rationalize, I get root 2 over 2. The cosine of 45, again, if I'm choosing this 45, 1 is also the adjacent. So in this case, your sine and your cosine are the same. And my tangent, regardless of which 45 you pick, would be 1 over 1, which is 1. Now when you want to evaluate the trigonometric functions of 30 and 60, it stems from an equilateral triangle. In an equilateral triangle, all the angles are 60 degrees, but I'm going to pull an altitude. So if I pull an altitude, this becomes 60, then this right here becomes in half, and this is how we get our 30, 60, 90 triangle. All right, for the purposes of making life easy, let's say that each side was 2. All right, and again, that's an arbitrary. Make it 4, make it 7, but I made it 2 because it makes my hypotenuse 2, and because I dropped an altitude, if this is 2, then this piece would be 1. And then I can do 1 squared plus, let's call it y squared equals 2 squared. 1 plus y squared equals 4. Y squared is equal to 3, so that makes this side root 3. All right, so when you want to find the sine of 30, here's 30. I need to go opposite of 30, which is 1, over the hypotenuse is 2. The cosine of 30, would be the adjacent side of root 3 over 2. And your tangent of 30 is going to be 1 over root 3, which after you rationalize gives me root 3 over 3. Now let's do the sine of 60. Opposite 60 is root 3 over the hypotenuse of 2. Things that make you go, Now let's do the cosine of 60. That's going to be adjacent over the hypotenuse. Things that make you go, All right, and last but not least, your tangent of 60 is going to be root 3 over 1 or just root 3. So, hey, what do we notice? We notice that the sine of 30 was equal to the cosine of 60. We notice that the cosine of 60 was equal to the sine of 30. So that's a pattern. Notice in the pattern, aren't 30 and 60 complementary? They are complementary angles. Complementary angles has a sum that is equal to 90 degrees. So we do have a pattern that they're called cofunctions. The sine and the cosine of two angles whose sum is equal to 90 degrees, they're always going to be equal. So like the sine of 15 would equal the cosine of 75 because those are supplementary. All right, let's finish this by talking about some application problems. This is a template. So keep this in mind. I'll try to like pinch in here. But this is how we are going to make equations, like little equations, when we have to find out one of the sides when perhaps we only know one side, not the other. So if you're going to solve a right triangle, solving a right triangle means you have to find all angles and all sides. So they tell us that A is 29 degrees. We know that C is 90 degrees. So all three angles have to equal 180. A and B specifically, if you use the complements theorem, they have to be complementary. So if I take 90 minus 29, we end up that angle B is 71 degrees. All right. Now that we know the angles, all right, we have been told that AC is 3 units. All right, we have to find the side of AB first or BC first. It really doesn't make a difference, but this is where the template comes in. All right. You have to pick an angle. It does not make a difference if you want to pick the 29-degree angle or the 71-degree angle, but you cannot pick C. So I'm going to pick 29 just because that's what they gave it to me. It is also your prerogative to determine if you want to find side AB or BC first. You guys, it doesn't make a difference. I'm going to go ahead and I'm just going to choose to find BC first. So what I say to myself, we figured out that the angle measurement was 29 degrees. All right, X is opposite. 3 is adjacent to 29 degrees. So when you think of SOHCAHTOA, that means opposite over adjacent is tangent. So we're going to use the tangent of 29 degrees is equal to x over 3. I'm going to solve both sides, and so we'll put 3 tangent 29 degrees in the calculator, and 3 tangent of 29 is approximately 1.7. And it is okay on these problems where they are not exact values, like there's no way to find an exact value of tangent of 29, to go ahead and give a decimal approximation. So this is where you have a couple of choices, and this is where you and your neighbor could differ by 100th or so in terms of how you round. You can find AB two ways. You can make another trig equation like we did before, or you can use Pythagorean theorem. So again, one way that you can go about finding finding AB is by taking AB, by taking 3 squared plus 1.7 squared equals AB squared. And friends, that's not wrong, that's not bad, but that was an approximation. So to maybe get a little bit more accuracy, I'm going to go ahead and make another trig equation. So I'm going to use the information that was given in the problem. Friends, you can choose 71 degrees. You could choose 1.7. But I'm going to just stick with 29 and 3, and now I'm going to find AB. So 29 in relationship to y, that's the hypotenuse. 3 in relationship to 29 is the adjacent. So if you have an adjacent over hypotenuse, so remember our template, we have 29 degrees equals 3 over y, that is going to be a cosine. So another reason I wanted to show it to you this way is in the previous problem, we had a variable in the numerator. So in the previous problem, our numerator was on top. But in this problem, our variable was in the numerator. But in this problem, our variable is in the denominator, so just want to kind of go over that algebra. So I'm going to multiply both sides by y to get rid of the rational expression. So I have y cosine of 29 equals 3, and now we're going to divide by the cosine of 29. All right, so I have 3 divided by the cosine of 29. And that gives me 3.4, and that answer should make sense. It should be the largest of all the angles. So this was approximately 3.4. All right, we're going to do one more application problem, and we'll call it a video. This particular application problem has to do with angles of elevation and angles of depression. And you know what? There is a big fat typo. That should be A-N-G-L-E, folks. All right, or angle of depression. I can't stress this enough. An angle of elevation or an angle of depression, they always contain a horizontal side. So if I consider this triangle in this orientation, this angle right here is an angle of elevation because here is its horizontal and the other side is going up. This is not an angle of depression. It is formed by a vertical. So you either have an angle of elevation or depression. You do not have both. If I want an angle of depression, I would draw my triangle in this orientation. And now I have a horizontal, and now I do have an angle of depression. Furthermore, I think it's helpful to denote, especially in a lot of problems, that I just tell kids always put your theta or your x by the horizontal, because for every angle of elevation, so here is an angle of elevation. If I make this into a rectangle, here's its corresponding angle of depression up here. See how this is being formed by a horizontal? And the relationship between the two, they are congruent. They are alternate interior angles. So a parasailer is attached to a boat with a rope 300 feet long. The angle of elevation from the boat to the parasailer is 48 degrees. Estimate the parasailer's height above the boat. All right, so we have a boat. Okay, I want you to think about, you have to use a little common sense. The parasailer is not going to be right above the boat. You've got a parasailer in the air attached to the boat by a 300-foot long rope. They tell you the angle of elevation from the boat to the parasailer is 48 degrees. An angle of elevation always has to be formed by a horizontal. So that's your 48 degrees. They want to know the height above the boat. So again, I use my template. I say to myself, if I look at 48 degrees, X is an opposite value, and 300 is a hypotenuse value. So what uses opposite over hypotenuse? The sine. So the sine of 48 degrees is X over 300. We're going to multiply both sides by 300. So we want 300 sine of 48. And the height of the parasailer is just at 223 feet. Okay, you are ready to do Unit 1, Lesson 1, Part 1 on your WebAssign. Enjoy.